Hello, let us begin by proving a propositional tautology. So I want to prove not P implies not P. So I know from the structure of the proposition that the proof must be a function that takes a proof of not P and produce a function which proves not P. So this proof must be a function that takes a proof of P and produces false. So at the moment, I have a proof of not P and a proof of P with me. So the only way I can proceed is by applying the proof of not P to something. So the proof of not P can take a proof of not P as input, which in turn must be a function that takes a proof of not P and produces false. So observe, I have three proofs with me: proof of not P, proof of P, and proof of not P. And I can apply the proof of not P to proof of P to generate false, and I am done. Let us try and prove double negation elimination. So we cannot prove this in constructive logic. So we need a tool from classical logic, which is called the law of excluded middle. So observe, it is a proof of P or negation P given a P which is a proposition. So here I am supplying it the P that we have. So I can apply R dot elimination on this, and on one side I have to take a proof of P and produce a proof of our theorem, which must be a function that returns a proof of P which I already have. In the other case, I have to take a proof of negation P and I have to produce a proof of the theorem, which must be a function from a proof of not P to a proof of P. So if you look at all the data that we have with us, we can apply HNNP to HNP to generate false, but we need a proof of P. This is easy to fix. We apply false dot elimination to obtain a proof of P. So this theorem called double negation elimination is only true in classical logic. So the use of excluded middle is necessary. We will now prove that P implies P using tactics. So tactic mode allows us to write proofs in a more English fashion. So we enter the tactic mode by using the word by. We use the intro tactic to introduce the left hand side of the implication into the hypothesis. Let's call this HP, and we have to conclude P, which we can do using a tactic called exact. So exact HP uses HP to prove the goal. Let us now prove P implies Q implies P using tactics. So we introduce HP, still have an implication in the goal, so we introduce HQ and we say exact HP. So observe that HQ is unused. We can replace it with an underscore. We can make the proof shorter by collapsing the two intros into a single intro with multiple variables. Let us prove that P implies P is P and P. So we introduce HP. The remaining goal is an AND. So we use the apply tactic with the theorem and.intro, and observe that Lean has split the proof into two cases. So what happened is it unified A and B with the goal P and P. And if you look at the hypothesis required by and.intro, we need a proof called left, which is a proof of A, and a proof called right, which is a proof of B. So this corresponds to the two remaining goals. So we solve each goal in turn. So the first goal we can solve by exact HP. The second goal we can solve by exact HP. So you need not use curly braces. You may also use bullet lists. Let us prove a more complicated tautology. So I want to prove P implies Q implies R implies P implies Q and R. We enter the tactic mode, introduce proofs of P implies Q, P implies R, and P into the hypothesis. Now we have to prove Q and R, so we apply and.intro to split into two cases. In the first case, we have P implies Q and P. We can specialize HPQ with HP to rewrite HPQ into a proof of Q. And now we can say exact HPQ to finish this case. For the second case, we can specialize HPR with HP. This converts HPR into a proof of R, and we finish the proof by saying exact HPR. Say we want to prove P implies P or P. We enter tactic mode, introduce HP. We can also write the proof in one line by using semicolon as a separator. So right now I have to prove an OR. So I have to apply one of the introducers for OR. And we can finish the proof by saying exact HP. Let us prove that not Q implies not P implies that P implies Q. This is not true in constructive logic, so we have to use classical logic. We introduce the left-hand sides of the implications into the hypothesis. After this, we can use have to prove an intermediate claim, which here is simply that Q or not Q holds. Now we can split the proof into cases using E and Q. We use the tactic cases for this. So observe that cases E and Q split the proof into two goals, case INL and case INR. So in case INL, we get a proof of Q, and we have to produce a proof of Q. In the case INR, we get a proof of not Q, and we have to produce a proof of Q. So we can specialize using H and Q, H and Q and P. So this will give us negation P in the hypothesis. Now we have both P and negation P in the hypothesis. So we can ask Lean to find the obvious contradiction and finish the proof. We can define a proposition for even numbers. So even n is a proposition which is there exists k, n is equal to 2 times k. Similarly, we have the proposition odd n, which is there exists k, n is equal to 2 times k plus 1. Since both of these are there exists statements, we will need exist.intro, which is a proof of exists P, where P is a map from alpha to propositions, where alpha is a type, here nat. And to prove exists P, we have to supply a witness of type alpha and a proof that P holds at W. Let's say we want to prove 0 is an even number, which we write as even 0. We use exists.intro, and we have to supply a witness that will satisfy k, and the equation 0 is equal to 2 times k. So to prove 0 equal to 2 times 0, we can use simple computation, and we can tell this to Lean by entering tactic mode and using the tactic decide. We can now prove that successor of an even number is an odd number. So if n is a natural, then even n implies odd n plus 1. We enter tactic mode, introduce the hypothesis that n is an even number. Now we extract from Hn the witness k and the proof that n is equal to 2k. Let us call them k and hk respectively. We can use the unfold tactic to unfold the definition of odd in the goal. This is not necessary, so we can now apply exist.intro and provide a witness. In this case, the witness is simply k. So observe that this can be proved by replacing n in the goal using the equation hk. So we use the RW tactic, which is short for rewrite, and give it hk, which is the rule to be used for the rewrite. Observe that the goal is now 2k plus 1 is equal to 2k plus 1, which Lean can see trivially. We can now prove that 1 is an odd number by combining the previous two proofs. So we have the successor of an even number is an odd number, and we have that 0 is an even number. Observe that we did not give the value of n to successor of even number is an odd number. So the reason is because we put the parameter n within curly braces, which tells Lean that it can figure out n automatically from the proof even n. We can prove the successor of an odd number is an even number using a very similar proof. The initial steps are as before. We introduce odd n into the hypothesis, obtain the witness k, and the proof that the witness satisfies the proposition. Then we apply access.intro with the value k plus 1. Then we rewrite the goal using the equation hk. So Lean is unable to see that 2 times k plus 1 is the same as 2 times k plus 1. This equality is slightly non-trivial. So we can tell Lean to use RFL, short for reflexivity, and it will be able to observe.